Hello and welcome to another video of Vidhai. In this video, we'll be looking into the chapter of atomic structures, where this chapter is important for the exam of NMMS. I'm Ryan, a volunteer of Vidhai for the team Exams Vidhai, where everything is possible. In this particular video, we'll be also looking into the contents of the video for now, that is, the introduction to this chapter, Dalton's atomic theory. We'll be taking a look into fundamental particles, that is, electrons, protons, and neutrons, and Thomson's atomic model. In the future videos, we'll be learning about valencies, chemical formulas, and laws of chemical combinations. And let's get started into the first video. So here is a pictorial representation of the chapter that we are going to study. For now, we are going to study Dalton's atomic theory, fundamental particles, and Thomson's atomic model. And now let's get started. So there are 118 elements so far that has been identified by us in this present Earth, all according to the textbook. That is, there's more than 118, but there is 118 according to the textbook, and that is what we are required to learn, and that's more than sufficient. Where 92 of these 118 elements that has been arranged in this series of table that is called as the periodic table is found in nature directly, that is like oxygen, nitrogen, calcium that is found in our bones, while other elements, the rest of the 26 elements are made by us. They are not existing in the nature in its pure form, like ognanesium, and you have this F block elements here that you'll be learning in the later stages of your schooling. Each element is made up of minute particles called as atoms. Those are the matters that you have studied before, right? These group of atoms form matter, but now we are going into the minute detail that whatever is made up of. So it is derived from the Greek word atomos, right? And tomos means the smallest divisible particle, and atomos means a smallest divisible particle. So the most smallest divisible particle in Greek is atomos, and the word atom is derived from atomos. Now we'll be going through John Dalton's and J.J. Thomson's atomic structures in this particular chapter. You'll be in the future learning about Rutherford's, Niels Bohr's, and Schrodinger's atomic structures as well. So these are a few names that have given a lot of contribution to the study of atoms. So with that being said, let's take a look into the first ever scientist that has given a great contribution to the atomic study. So Dalton's atomic theory states that all matters are made up of extremely small particles called as atom. We have made this fundamental in the previous slide as well. Now here the atom representation of Dalton is just a spherical ball. It's just there, and it's not colored. It's colored for our representation for us to understand easily. I'll tell you why it's colored later. So all atoms of different metals and elements. So you have water, you have oxygen and hydrogen. Those are two different elements. You have iron, you have copper, which are two different elements as well, and they as in an atom form won't be looking similar. So you have this gray color ball which is enlarged and this blue color ball being diminished. So these two are different atoms, and we can well and say that these two are different elements as well. Atoms can also vary in size. We'll be looking that in your future schooling. And atoms can be neither created nor destroyed. Like, this is the most important feature that Dalton pointed out, and later it was proven to be wrong, but that we'll take a look into later. For now, there's another feature that we need to take into, that all atoms and elements will combine in a fixed ratio to form a certain molecule. So you have water having one oxygen and hydrogen of 2 in number. So 1 oxygen plus 2 hydrogen gives water. An atom is the smallest particle of matter that can take part in a reaction. So If you have anything smaller than atom and if you combine them together, they won't actually combine. But if you take one oxygen atom and two hydrogen atoms, the smallest particles that you can take and combine, you are bound to get a water molecule. The limitations of Dalton's theory is more or less the demerits of Dalton's theory. So, atom is no longer the smallest individual particle. Inside an atom, you'll find this orbital structure that you might see in various textbooks and various internet sources. That you have these small balls going around this core that is made out of two different colors, right? So this atom is made out of three different particles among itself, and atoms have same element but can also have different masses. These are usually known as isotopes that you might have learned that in your earlier classes. And not always atoms, when arranged in the same manner, will form the same object, but arranged in a different manner will form a different object. So you have diamond here and you have graphite here. Diamond is something, a precious jewel, and carbon is something that you find on the tip of your pencil, but they both are made out of carbon. Fundamental particles. So we'll be taking into one of the scientists who had actually sparked an innovation in fundamental particles, that is Sir William Crookes. What he did was to set up a vacuum tube. Inside there were two electrodes, a cathode and an anode, like this, right? And then when he passed on a voltage across these cathode and this anode, he saw a little visible rays traveling in straight line from cathode to anode. Now, why do I say this? These rays are nothing but the electrons that you see in the atom that I have shown you. So, you can see this image, right? So, this image has these blue dots going across this core. These blue dots are the electrons which are revolving around the core, and the core is called nucleus. So, in this particular setup, what we do is pass on a voltage to cathode to anode, but in the anode we'll have a small gap left out. So when the rays hit these anodes, it will miss the anode and go still in the straight line and hit this fluorescent material. Fluorescent material is something when a reaction takes place, or if it reacts with anything else, like in terms of physics as well, physical changes, that is, it will be visible to us. So we have seen fireflies which have fluorescent material in them. So this cathode ray, when it hits the fluorescent material, which is usually transparent, will give a glow of light. So we do know cathode rays exist. Cathodes always travel in straight line from cathode to anode. This travel in straight line is important, and cathode rays are made up of mass and kinetic energy, meaning they are something that exists in the physical world as well. They are not imaginary and they do follow the laws of physics. This is basically the meaning of the second point. The third point states that it is negatively charged, that is, on an electric field, it is deflected towards the positive side, meaning they are negative charged particles. The nature of the cathode ray do not depend on the nature of gas filled inside, because we technically filled out the gas from the vacuum to form vacuum rather. So cathode rays does not depend on air at all. And now for the protons, what did Goldstein do is did a similar setup to this cathode ray tube, this Crookes ray tube, right? But instead of a fully dense cathode, he did a perforated cathode, meaning it's porous, it's more or less not working efficiently. And instead of vacuum, he pushed in air at a very low pressure, so you got a little bit of air. And what does this do is he saw visible light rays, or I shouldn't say light rays, but rather rays as well, rays coming from anode to cathode in a straight line. Before we saw from cathode to anode, now we are seeing from anode to cathode. And same, these rays are called anode rays. Anode rays travel in straight line and are also made up of material particles, meaning they have both mass and energy, following the laws of physics, and is also deflected toward the negative side of the electric field, meaning they are positively charged. Anode rays does depend on the nature of gas that is inside the tube, while cathode rays don't. Now in this image you will be seeing that these blue color dots that we have been looking at is the electrons, and these red color dots that you see in this core, the nucleus, is the protons. Now you may ask me a question, what is that other colored dots we see, the black color ones, the gray color ones, what are those? We'll be looking into that now, and those are particularly called as neutron. So what did James Chadwick do is set up an experiment to prove that neutrons do exist. These neutrons provide stability to this atom so that things actually exist for a reason. So neutron is a neutral particle. It has mass, it has energy, but it has no charge, meaning it follows the physical laws. But when you expose it to magnetic or electric field, it's not deflected, meaning it's neutrally charged. So here's an enhanced image of the atom that we have been talking about. See, these blue color dots are called electrons, and these are negatively charged. The neutrons are these orange color ones. For this pictorial representation, we are taking the neutrons as the orange color ones, which are not charged, they are chargeless, and these protons are gray color charged here. Notice that neutrons and protons are same inside the same core as clustered up together. That cluster is called as nucleus. Now, to go forward, we'll be learning about J.J. Thomson's atomic model. Like this, after the discovery of electrons and protons, J.J. Thomson had a say in this atomic structure study. So, what did he do was take a watermelon, and if you cut it in half, you can see seeds into them, right? So, imagine the red color part to be the positive charge and the seed part to be the electron part. Now imagine it as a spherical shape, and it's an atom basically, so it has both positive and negative charge. This model was later known as plum pudding or watermelon model, and the radius of this particular sphere that J.J. Thomson was proposing was in a matter of nanometers and Armstrongs. But the drawbacks of J.J. Thomson atomic model that he has failed to mention why these positive and these negative charged particles are not interacting with each other. So for your quick information, when you have a positive and a negative charge together, any object, right, they would attract to each other and then they would combine together to form a neutral charge. Here you can clearly see the positive charge, the red color part, is in contact with the gray color part here, and even though it's in contact, it's not getting neutralized. So why is that? That J.J. Thomson did not say, and his theory contains only protons and electrons, and he failed to mention the presence of neutron. So why J.J. Thomson model was important to us? Well, this was among the first models that was widely accepted before a new one came, and also gave a head start to how an atom was looking as. So for this video, we'll be ending up with a small question. So it's based on this previous slides that we have been seeing. So question number 1 is, cathode rays are made up of whether it's neutral particles, positive particles, negative particles, or none of the above. I'll be waiting for some time. You can pause the video and answer to yourself, or you can continue watching this video to see the final answer. Right, so the answer to this question is negatively charged particles. In the slide of cathode rays, where we learnt about CRT, which is the short form of cathode ray tube or Crookes ray tube, we seen that the cathode rays are negatively charged and anode rays are positively charged. This concludes the first video of the chapter Atomic Structures. Do check the description of this video for extra questions and lecture notes for this particular chapter. All the text that you see here are from the textbook only, so you don't have to worry, you can go through your textbook again, and the images are from your textbook, somewhere from your textbook, somewhere from your internet sources like Google Images. And do remember to go through the points to remember and glossary at the end of the lesson in the textbook. And as always, I'll see you guys in the next video of this atomic structure video. Thank you for attending.